Okay, they're made from metals only, and what you're going to see is you're going to see just the metal written, like Cu, copper, or you might see Hg, mercury, or you might see Mg, magnesium. All of these are just metals, and if you see the element just by itself, it has metallic bonds. Metallic bonds are so easy, you're going to be like, really, is that it? Yep, that's it. So what type of bond does silver have? Metallic bonds. What kind of bond does sodium have? Metallic bonds. It's a metal. It's on the left side of the periodic table. And it's bonded sodium to sodium to sodium to sodium with metallic bonds. Now, all metallic substances have luster. They are malleable. They are ductile. Whoops, I crossed the wrong T. Okay? And they do something very, very important. They always conduct electricity. Even as a solid. Metals conduct electricity. Why? Because they have what we call a sea of mobile electrons. What that means is that the electrons are constantly moving in order to complete the octets. Electricity is nothing more than either moving ions or moving electrons. In an ionic bond, the ions were locked in a crystal solid, but as soon as you expose them to water, or as soon as you liquefied them, then the ions were able to move around and conduct electricity. With metals, they don't need to be liquefied because the electrons are able to move from element to element. Let me give you an example. I'm just going to draw it on the next page so you can see what the heck I'm talking about. Let's say I have magnesium here. Magnesium has 2 valence electrons. And this magnesium also has 2 valence electrons. And this magnesium has 2 valence electrons. And this magnesium has 2 valence electrons. I just wrote them on different sides so that it made my life easier when I'm moving them. This first magnesium says, hey, I want 8 valence electrons. So this magnesium says, all right. Ooh, I took the G with me. He gives him 2. And this guy gives him 2. And this guy gives him 2. And now he has a complete octet. Well, these electrons, okay, now move as a unit to the next magnesium, to the next magnesium, to the next magnesium, and they keep going back and forth. And if there were more magnesiums out here, they would constantly be moving around to complete the octets. Because the electrons are constantly moving, a sea of mobile, moving electrons, this substance, this metal, can conduct electricity even as a solid. It doesn't have to allow its ions to move around. Okay? Any questions about metallic bonds? No. The hardest part is going to be recognizing them, and that is, let's say they write silver down, and they say, what kind of bonds does it have? You're going to say metallic bonds, because it's a metal, and there's only silver there. Somebody's going to ask me, well, what about if there's 2 different metals and they're connected to each other? That's not called a metallic bond. That's called an alloy. An alloy is 2 or more metals combined. Like tin. I lied. Sorry. Brass is tin and copper. Brass is an alloy. It is not found on the periodic table. It is a combination of 2 metals, tin and copper. All right, any questions about metallic bonds? Because that's pretty much done. So right now we have done ionic bonds, we have done covalent bonds, and we have done metallic bonds. Ionic bonds are a metal and a nonmetal. You know this already. Covalent bonds, 2 nonmetals. And then metallic bonds are metal only. Any questions? Okay. Ionic only conducts when it's liquid or aqueous. Covalent never conducts. Metallic always conducts. All right. All three of these types of bonds are called that's not how you spell it, Kaufman. Intramolecular. Intra means within the molecule. They are intramolecular. We are now going to talk about intermolecular. What does inter mean? Nope, this one's inside. Intra is inside. The ionic bond is inside that compound. The covalent bond is inside the compound. The metallic bond is inside the metallic bond. If I said I'm going to drive Interstate 95 all the way from Maine to Florida, what does that interstate mean? I'm going across states. I'm between the states. Okay? Now, there are intermolecular forces of attraction, which are things that are holding molecules to other molecules. I'm going to highlight, you can underline. The I, the M, the F, and the A. And I'm highlighting them because if I had to write intermolecular forces of attraction every single time I said it, it would take forever. So what I'm going to do is I'm going to abbreviate it IMFA. Intermolecular force of attraction. Okay? And there's going to be 4 main types of intermolecular forces of attraction. We're going to start with, I'll just start. Okay? The first intermolecular force of attraction is called a dipole attraction. So let's look at what the word dipole means. Di means 2, poles. So a dipole is a fancy way to say polar molecule. That's not an M. If I say this is a dipole, then you know it is a polar molecule. That's it. So if I have dipole attraction, I'm really saying polar molecule attracted to another polar molecule. That's what a dipole attraction is. Polar molecule to polar molecule. I'm going to draw one for you. Ta-da! Not as exciting as my uranium glass, but here we go. HCl, hydrochloric acid. HCl, hydrogen chloride. Is this molecule polar or nonpolar? Polar. It is asymmetric. If I divide it down the middle, this side is different than this side. It is a polar molecule. And because it is polar, we can call it a dipole. It has 2 poles, a positive pole and a negative pole. In this molecule, which side is positive and which side is negative? Yes, sir. The chlorine is negative because chlorine is stronger than hydrogen. So these electrons are slightly closer to the chlorine than they are to the hydrogen. I really did waste a whole period, didn't I? It was very interesting. I want you to... Hang on. There we go. All right. So, fancy word for polar molecule is a dipole. And the other... I lost my train of thought. So now we've got hydrochloric acid. We know it's a polar molecule. If I take two hydrochloric acids, and I know this and this side is negative and this side is positive, and I take another one and I put negative and positive. Notice I'm putting them in circles now, because it's not the charge. It's just telling us which side of the molecule is a little bit more negative and which side's a little bit more positive. If this molecule is floating around and this molecule is floating around, eventually there is going to become an attraction between the positive end of one molecule and the negative end of the other. So this is a dipole, and this is a dipole, and they're attracted to each other, so we call this a dipole-dipole attraction. I know. They are in love. I'll draw some hearts. This is not a bond. This is an intermolecular force of attraction, because here is the molecule, and here is another molecule. They are two molecules that are attracted to one another, holding on to one another. They are not intramolecular, not inside the molecule. It is between the two molecules. Dipole-dipole attractions occur between two molecules. Okay, does everybody have that or understand that? Okay, let's move on. The next one, do you need to see that again? Okay, go ahead. The next one is a stronger type of dipole-dipole attraction. It is called the hydrogen bond. I'm going to write the word hydrogen bond out. It is not a bond. It is an intermolecular force of attraction. IMFA. Okay? It is not a bond. It is not inside the molecule. It is between two molecules. Okay? With the hydrogen bond, it is stronger than a dipole-dipole. And I'll sum this all up at the end. Okay, it is stronger than a dipole-dipole. And when I talk about intermolecular forces of attraction, I want you to think hugs. Hugs. Just hugs. Oh. Have you ever hugged a kitty? A little kitty cat?
Wow.
Okay, and you just hold it and it's like that. And somebody's like, give me the cat, and they take it right away from you. Okay, because they're like, you're weird. You're hugging a kitty cat. And then, have you ever hugged a grizzly bear?
Yeah.
Not yet. And somebody tries to rip you away from a grizzly bear. Which one's going to give you stronger hugs, the kitty cat or the grizzly bear? The grizzly bear. The grizzly bear is going to be harder to get you away from the grizzly bear than it is for you to be torn away from the kitty cat. Okay? The stronger the intermolecular force, the stronger the hug. The harder it is for you to get away. So when you have solids, your intermolecular forces of attraction are very strong. These molecules that are making up the tabletop here are hugging each other very tightly. I can't get them apart. I can't move them. But if I'm in liquid water, my intermolecular forces of attraction are a little bit less because I can move those pieces or those molecules apart from one another. Okay? The stronger your intermolecular forces of attraction, the higher your boiling point is going to be. It's going to be harder to rip them away. I will write that down in a few minutes. Okay? Let's just talk about what types of things will form hydrogen bonds. I'm going to start with the strongest hydrogen bond, HF. Should make sense because fluorine is a pretty darn strong element, isn't it? And this side is negative and this side is positive, and it is a polar molecule, just like we looked at here. If I take another hydrogen fluoride and I bring it near, there is an attraction between the fluorine of one and the hydrogen of the other. That is a hydrogen bond. How is it different than this guy? Hydrogen bonds only form between the hydrogen of one molecule and the fluorine, oxygen, or nitrogen of another molecule. That's the key, okay? So hydrogen bonds only form between the hydrogen of one molecule. What's going on back there? Your pen is dropping. And the fluorine, oxygen, or nitrogen of another molecule. So do you see how the hydrogen here, the hydrogen of one molecule, that's the hydrogen of this molecule, is attracted to the fluorine of this molecule? That's the hydrogen bond. There is no hydrogen bond here because it's the hydrogen to a chlorine. Hydrogen bonds only form between hydrogen and nitrogen, oxygen, and fluorine. Fluorine being the strongest hydrogen bond because fluorine is the strongest or highest electronegativity. Okay? Hydrogen bonds are responsible for the high melting point and boiling point of the substance. So HF needs a lot of energy, a lot of heat to get it to boil because it's hugging very tight. It is a very strong intermolecular force of attraction. The stronger the hug, right, an intermolecular force is just a hug between two molecules. The stronger the hug, the harder it is to get them apart. And you have to put in more and more heat energy or light energy in order to get them to separate. Okay, let me draw the other two. Water, wow, that's sloppy. Try that again. Water has hydrogen bonds. Put exclamation points. Draw a picture of something very special to you. Like, oh, now it looks like a pig. Wait, I'll make it a pig. It wasn't supposed to be a pig. It was supposed to be a cat. Okay? But it looked like a pig because I drew a curly tail. That's how you're going to know it's important. Okay? Water has hydrogen bonds. So here's a water molecule. It is a dipole. Does everybody agree that it is a polar molecule? Water is polar. And the oxygen side is negative and the hydrogen side is positive. This is a dipole. Another water molecule comes along. There is an attractive force, an intermolecular force between the hydrogen of one to the oxygen of the other. Here's a molecule. Here's another molecule. They are not one thing. They're individual molecules. And there is an attractive force between them. That's the hydrogen bond. Water has a very high melting point and a very high boiling point. 0 degrees and 100 degrees are fairly high melting and boiling points. Why does it have high melting and high boiling points? Because it has strong intermolecular forces of attraction. IMFA, intermolecular forces of attraction. Who's going to have a higher boiling point? HF or water? Try again. HF. Because HF is a more polar molecule. Okay? But the Regents will probably ask you about water. Water has hydrogen bonds, and it is responsible for the high melting points and high boiling points. That's what makes water boil at 100 degrees. Otherwise, water would boil at like negative 20 degrees, something ridiculous like that. And all the water on Earth would be a gas if we didn't have this, because it would already have boiled off at our temperature. All right, the last hydrogen bond example that the Regents uses is ammonia. Now, you know why you needed to be able to draw these, because I'm not going to spend time learning how to draw them. You need to know how to draw them. Okay, here's two ammonia molecules. The nitrogen is negative where the hydrogen side is positive. And there is an attractive force between the hydrogen of one and the nitrogen of the other. So again, here's a molecule. Here's a different molecule, and here's the force that's holding them together. This orange that I just drew is the hydrogen bond. It's generally denoted with a little dotted line because it's not a bond. It's an attractive force between the two molecules. So there's three molecules the Regents uses to show hydrogen bond. HF, which is the strongest, water, which is the middle one, and ammonia, which is the weakest of the three hydrogen bonds. And see how they're listed on the periodic table? It's N, then O, then F. F is the highest electronegativity. N is the lowest of the electronegativities for those three elements. And O is in the middle. Okay? All right. Does everybody get this? Dipole-dipole attractions are just any old polar molecule. If the polar molecule happens to have H's and F's, H's and N's, or H's and O's, then it's got a special name because it's stronger, and that is a hydrogen bond. Okay, last, well, not the last one, but close to the last one. All right, this one is called a van der Waals force. It's German. Sometimes it's going to be called a London dispersion force. I'm giving you that because every once in a while that shows up on a question, and I want you to know that it's the same thing. These are exactly the same. Okay. The Regents will call it a van der Waals force. That's what they'll call it. But some questions that I'm going to give you, we're going to call it London dispersion forces. They're the same. Don't get confused. Okay? So a van der Waals force happens when you have a non-polar molecule. A non-polar molecule does not have a positive or a negative side, so it doesn't act like a little magnet. Like the other ones were little magnets, right? A positive side and a negative side. Well, these guys don't have a positive or a negative side. The electrons, and this you don't have to worry about, I'm just going to tell you the background here. These electrons are moving like this. And so when they're moving like this, even though they're in the middle, and I've told you they're right smack dab in the middle, they're really just vibrating. And when they vibrate, sometimes they're to the left and sometimes they're to the right. So left, right, left, right, left, right, left, right. Sometimes they move like that. When they move to the left a little bit, this side becomes a little negative, and when they move to the right, this side becomes a little negative. Those are called momentary dipoles. In other words, they are becoming negative, then positive, negative, positive, negative, positive. For all intents and purposes, I want you to think of these as having no positives and no negatives. So, if they're not acting like little magnets, Do they want to be near each other? No, they have no reason to attract each other. So if I had two hydrogens, if I had hydrogen bonded to hydrogen and I had another molecule of H2 and H2, these guys don't want to be anywhere near each other. And so this guy's going to wander off. When the molecules are not near each other, and they've wandered off and got as far away from each other as possible, that's a gas. Hydrogen is a gas at STP. At regular room temperature, hydrogen is a gas. Can I force hydrogen to be a liquid? How can I get them to be attracted to each other? How can I make them like each other? What types of things can I physically do to make them get closer to each other? Lower the temperature. Low temperature. What else can I do? I can increase something. Increase the pressure. I could push them together. I could be like, hydrogen, get your butt over there. And this hydrogen would go, all right. And it would go over there. Okay, this is not a strong intermolecular force of attraction. Because the minute I stop pushing hydrogen into that corner, hydrogen's going to be like, I'm out of here. And it's going to start spreading out again. Gases have weak intermolecular forces. Solids have strong intermolecular forces. Okay? In order to get a gas or something that is nonpolar to be attracted to the other molecules, we need to do these things. We need to lower the temperature, get them cold, so they're just moving just a little tiny bit, and we have to push them together with pressure. If I want particles to spread out as far apart from one another as possible, then I would do the opposite. I would increase the temperature and I would lower the pressure. Do you understand what I'm saying, or am I just speaking Greek? A little bit of both. Okay? So if I want these particles to be close to each other, think about if you got really cold and I locked you in a freezer, which would be terrible. But I locked all of you in a freezer. What do you think would start to happen? Yeah, well, before you die, before you get hypothermia, what would happen? You would start to get like smaller and smaller, try to conserve your heat, right? And then you would start to shiver a little bit, and then you might be like, I'm just gonna snuggle up to the guy next to me because you would get a little bit cold, right? So if I put you all in a freezer, that's what's happening. If I get it cold, these guys start snuggling up to each other so that they can stay warm. Okay? If I lower the temperature, they're going to get closer to each other. If I put you in an oven, oh God, this is just a terrible lesson. If I put you in an oven, first I put you in a freezer, then I put you in an oven. Okay, let's not do oven. Let's say I put you in Florida, where it's like 102 degrees and 100% humidity. So it's really hot. Okay? And somebody comes over to you and gives you a hug and stays there. Are you going to be happy about that? No, you're going to be like, get off of me, you crazy person there. All right, so it'd be like spreading out, trying to get as cool as you possibly can, right? So the hotter you get, the further apart these particles are going to be. Warmer temperatures, particles spread out. Colder temperatures, particles get closer together. Does that make sense? Okay? So if I want these guys to have attractions, if we want love to go on right here, look. Love. We want them to be close to each other. We need to get them low temperatures, and we need to push on them. Like, go love that person. Go love that hydrogen over there, right? I pushed it. You see what I'm doing here? Okay. All right. Oxygen. Oxygen is also a nonpolar molecule. Oxygen has van der Waals forces. What kind of attractions does carbon dioxide have? Is carbon dioxide polar or nonpolar? Nonpolar. If you have nonpolar, what kind of attractions are you going to have? Van der Waals forces. Is carbon dioxide a solid, a liquid, or a gas at STP? It's a gas. It's nonpolar. It's going to spread out. They want nothing to do with their carbon dioxide friends. Can I get carbon dioxide to be a liquid or a solid? What would I have to do to it? Lower the temperature, dry ice, increase the pressure. So you put it in a container, they increase the pressure, and it gets really, 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 really cold, and you make dry ice, and you've got solid carbon dioxide. Okay, now, don't give up on me yet. Does anybody know what this is? We've seen it a few times this year. Methane. Methane is... Oh, this is my favorite thing to do. Wait a minute. You know what that is? It's a cow. Good. Those are his horns. He's a bull. He's not a cow. He's a bull. Okay, so... Methane, right? Cow farts. You heard about this. Okay, so that's methane. That's cow fart. Okay? Methane is a small molecule, pretty small. It's only got 1 carbon and 4 hydrogens in it. Okay? Just so you know, this is like taped for eternity so you can see my cow fart. Okay? Now we're going to draw another one. I'm going to draw another molecule. Oh, this is red. This one's not as fun to draw because it's not cow farts anymore. That's a good question. I don't know. Okay? So here's another one. Is this polar or nonpolar? Nonpolar. Okay. So if we want to put methane up against another methane, I'd have to do what to it? Lower the temperature and increase the pressure. So I usually get methane gas, right? Methane is a gas. All right, now let's do this one. Is this polar or nonpolar? This one right here. Nonpolar. It's still symmetric, right? Symmetric. We check it for symmetry. Okay, so it's also nonpolar. So these are both nonpolar. I'm not going to write it twice. Okay. This is propane. Yes, I should have drawn the grill. I should have drawn the grill with a hot dog on it. That would have been fun. But, okay, isn't that a grill? Something like that? Oh, like a wine glass? No, that's a grill. Wait a minute. Wait, I have to draw a hot dog. It's a hot dog, guys. It's a hot dog. What? It's not red. Hot dogs are like a brownish orange. I don't have the color of a bun, but here's a bun. I don't know. It's a hot dog and a bun. Don't you like your buns toasted? All right, so propane. Hey, listen, you got to remember it. Propane, when you buy it from Home Depot or you buy it from Agway, how do you buy it? In that cylinder, right? You take the little gray cylinder and you go over to Agway and you get some propane. But they're selling you liquid propane. Why is it liquid? They pressurize it, don't they? And then as soon as you go home and you open the top, all the gas comes out in the form of a vapor, a gas. It comes out because it doesn't want to be near each other. All right, one more. Oh, brother. That's the bun, Joe. That's the bun. Whoa. Whew. You don't have to draw this. This is a big one. You'll draw them in the end of the year. You'll have to draw these. Okay. All right. So let's guess what this one is. First off, can we agree that the size of my molecules are getting bigger? Okay. So if the size of my molecules are getting bigger, remember my bear and my kitty cat, which one is going to have the stronger intermolecular forces? The bigger the molecule, the stronger the intermolecular forces. The bear has more hugs or stronger hugs than the kitty cat does. Okay. So let's try to guess what this is. First of all, is it polar or nonpolar? Nonpolar. Okay, it's nonpolar. It's symmetric. Guys, give me a second. I want to finish this today. Okay? If I divide it in half, I'm going to get the same on both sides. If I divide it in half top and bottom, I'm also going to get the same on both sides. So it is symmetric, which means it is nonpolar. And we can all agree that if you have nonpolar molecules, we're going to have van der Waals forces. Okay? All right. This stuff, that's me driving my convertible. You're going to see me in my convertible more times than not this year. What do you put in a car? Gasoline. This is octane. Oct because it has 8 carbons. Ane because it's an alkane. All right, so anyway, this is octane. When you buy gasoline and you put it into your car, is it a solid, a liquid, or a gas? It is a liquid. It is a liquid even though, stop talking, even though it has nonpolar molecules. Because the molecule is big enough that the hug is strong enough between the molecules to keep it a liquid. However, if you left gasoline out in a bucket, uncovered, it would turn into a gas pretty quickly. Not as quickly as propane, and not as quickly as methane, but it would still turn into a quote-unquote gas. Even though we call this gasoline, it's not a gas. It's a liquid when you buy it. And if you spill it, it vaporizes. It turns into a gas very easily. As the molecule gets bigger, the intermolecular forces get stronger. And the boiling points get higher. That is extremely important. The higher or the bigger the molecule, the stronger the intermolecular forces, the higher the boiling point and melting point. That's the last thing we're writing down today. The higher I should say the stronger, not the higher. Let's change that to stronger. The stronger the intermolecular force of attraction, the higher the boiling point. Bigger molecules have stronger intermolecular forces of attraction. And we'll pick up on that tomorrow. Okay? Remember, intermolecular forces are nothing more than hugs.